All right, good morning. Well, this lecture, we're going to keep extending ideas in chapter 6 and make progress on getting a flow field really clearly depicted. This is, as I've mentioned before, this is a pretty big area for mechanical engineers where you model flows. All sorts of applications. The ones I'm most familiar with are trying to come up with the best possible pump or fan that you can. A lot of people who work in it do drag, so working on drag. So take an example where someone might do this sort of work that we've been talking about with streamlines. This is a result of some modeling of fluids, and there may be three main points to look at here, and that's the front of the car, over the top of the car, and also the rear of the car. So at the front of the car, we got these streamlines coming, and you can see the stagnation point there. And at that stagnation point, we'd be interested in what kind of pressure is acting, because that pressure is going to create drag. Over the top of the car, we'd be interested in whether the flow was laminar or turbulent. Two big words we want to come out of these class understanding details on. A laminar means smooth or layered flow, and it looks like this car is pretty well shaped. Those fluid layers end up being one on top of the other. We don't have much rotation, we don't have much swirling, etc. Okay, and then at the end, we want to take a look at what's going on behind there. And again, some of the questions we've been asking with fluid flows is whether there is any sort of dilation, and is there any sort of rotation? And clearly we've got both going on at the back there. And that would be an example where someone who's doing some fluid modeling would be say, hey, what can we do to reduce that rotation? What can we do to reduce that dilation? All right, so what we're going to do today is get you some more practice on that, get a little bit better at it, and then add another type of line to the drawing. And those can be thought about as lines of equal force or equal pressure, lines that drive the flow. So to give you a really simple example that we'll be able to do clearly in a little bit, I've got a drawing there like that of a flow field. It's not super clear, but hopefully you can bear with me. If you look down below, we've got the legend there, and the streamlines are given by green. So I added some green in there to get the streamlines. And we have flow that's essentially flowing down and then taking a turn and going that way. So if you take a look up close, you can see that. You can see actually that as it makes the turn, the flow is slowing down. Those velocity vectors are getting shorter, and then it's going over the right here. So again, we have flow that's going down, 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 making the turn and going to the right over there like that. Okay, what about the lines that we're adding if we take a look at the legend down there? Okay, and so that is our goal today. One of our goals today is to come up with those lines. They're in red, and sometimes they're called the equipotential lines or the velocity potential lines. Okay, and I only have three highlighted in red, but you can think of this red line, one of these red lines here, as kind of like a push line. It is a line where there's equal push, pushing the flow perpendicular at each point. And if you take a look, those red lines are perpendicular to the green lines at every single point. And if you think about physically, if you're doing some design or doing some engineering, what would be the value of those equipotential lines? Well, those can tell you pressure. And of course, pressure is huge for fluids. So we want to be able to add something to our drawings. Okay, we want to be able to come up with the streamlines. We want to come up with velocity vectors. We'd also at times like to come up with acceleration vectors, and then we would like to come up with the equipotential lines or the velocity potential lines, and those are going to help us with figuring out pressure. By the way, on this topic, it does build on chapter 4. You can look at the results for test 1 and see how you did in the chapter 4 problem. A lot of you did great, fantastic. Some of you didn't. Hey, it's progress, so we want to try to keep getting better at it. Encourage you to go, if you had trouble, encourage you to go back to chapter 4. All right, so the first thing we're going to do is to do this type of work where we do this modeling, it is vector calculus. And so we're going to start by reviewing a little bit of multivariable calculus. All right, well, the first thing we want to do is review just a little bit more of multivariable calculus, vector type calculus. And what we've done so far is we've started with multivariable function and we've done derivatives. But we also need to be able to go backwards and essentially do antiderivatives. So that's something you're familiar with. I want to just get at it with an example. So I encourage you to write this example down, example 1 here, where I've given you, we're looking for a function of x and y, and I've given you the 2 partial derivatives. So we've got the derivative with respect to x is 3x squared plus y, and the partial with respect to y is x plus 3y squared. So go ahead and write that down. You certainly are welcome to see if you can do it in your head and come up with the answer. I'm going to be a little bit more systematic in my approach and do it on the whiteboard. So if you want to take a look at my first step and see if you can finish it off, I encourage you to do that as well. All right, so let's get going. So taking a look at it on a whiteboard, the classic approach is to go ahead and do one antiderivative at a time, or work backwards 1 step at a time. So there's that function. Okay, and we want to come up with, hey, what's the function when we do a derivative with respect to x? A partial with respect to x gives that. So I'm just going to write that down below. There's the function. Okay, and let's just go step by step. To get this, obviously we would need x cubed. To get this, we would need xy or yx. You can write it in either order. This will work because when we take the derivative of xy with respect to x, we treat the y like a constant, and so that we will get with that result. Okay, that's pretty good, but we could also have something at the end. So maybe we could have a plus 4, because if we do the derivative with respect to 4, then we're going to get 0. Okay, we could also have something else. Okay, we could also have a y. Okay, because if you do the derivative with y with respect to x, that's 0 as well. So this part right here is really good. I mean, that's a really good first step. But strictly speaking, we're supposed to consider the possibility that we could have these 2 terms here like that. And one classic approach that's used in a lot of calculus, multivariable calculus textbooks is to say, and hey, in addition, that 4 plus y could essentially be some sort of function purely of y. Purely of y. All right, so there's our first step. We now have a function that when we do the derivative partial with respect to x will give us this stuff here. Okay, and then the next step is actually to go through and take care of the partial with respect to y and see what the function is going to look like with that. So I had up that example I had earlier is the partial with respect to y was equal to x plus 3y squared. Okay, and we're going to go backwards and do that. All right, so there's my function, and there's my partial right there. And what would I need to go to write down to get a partial of x? Well, that obviously would be xy. Okay, and then how about 3y squared? I would need a y cubed. Okay, and hopefully you can recall that just from the previous example, I could have like a 6 here or some sort of constant, and I could also have something with an x in it. So in addition, I could have something that was purely a function of x, purely a function of x. All right, so putting it all together, the classic thing to do is to say, well, look, we need all these terms. I need an x cubed, I need an xy, I need this term right here, which fortunately is the same, and I need a y cubed there like that. So we essentially combine and get that all together. So I'll do that in a different color and write it up over here on the right side of the whiteboard. Our function, it's got to have a x cubed in it. Sorry about my hand. It's got an x cubed in it. It's got to have an xy in it. Okay. It's got to have a 3y squared, pardon me, a y cubed in it. Okay. And then after that, we think about these 2 terms. That's one approach. What if we had another term with a y in it? Okay. And I'll just put something arbitrary up there, like y to the 7th, be sine y or something like that. Well, is that going to work, right? If I take the partial of this with respect to x, I get 3x squared. Bingo, that's good. I get y, that's good. And for this term, I get 0, that's good. And for y to the 7th, I get 0. So this function right here works great for this one, for this partial right here. But how about the y partial? Does it work for the y partial? So here we go. X cubed, that's 0, that works. xy, I get x, that's good. Pardon me, and y cubed, I get 3y squared. Y to the 7th, though, I would get 7y to the 6th, and we don't want that there. So we're not going to throw on some sort of additional function of y. And if you reason your way through it, you can also see that we're also not going to throw in some additional function of x. We're not going to throw some additional function of x. So there is our answer, almost. There is one thing that we could add in there that would work, and that would be some sort of constant. So that is the sort of level of difficulty we're going to do in this class. We primarily, or almost exclusively, are going to be talking about functions of x and functions of y, and we're going to go backwards and try to, from the partials, and try to get the function. Okay, so back to the fluids. What we're going to go back to now is practice a little bit more about this stream function and try to give you an idea of what's going on. So the practical question would be, for example, if we're designing a pump. So this might be the inlet pipe to that pump. So that pipe is bringing water in. The vector lines represent water. And this would be the impeller where the water hits and goes out like that. Okay, so what is that going to actually end up looking like if we did streamlines? Well, obviously this one here is going to curve and go somewhere like that, and that one there is going to curve and go somewhere like that. We're going to have the exact opposite situation over here. Okay, and it's kind of interesting to think about what that middle one's going to do. We're going to get some stagnation at this point, and that might be worth thinking about. So my drawing's not great. This should be perfectly symmetrical, etc. But how about the equations of these lines right here like this, so we can get some sort of diagram up there and start analyzing what's going on. Okay, well, last time I introduced the idea of a stream function, and I'd like you to think about what's on the right side of the stream function as essentially a streamline expression. And that's the utility of it. If you remember when we did streamlines earlier, to take an example that we talked about, we got a streamline that might look something like this. Y is equal to C over X. Okay, y is equal to c over x, and we'll have multiple streamlines within our drawing, and the way we get the different streamlines is varying this value of c. Make c equal to 0, make c equal to 1, make c equal to 2, etc., etc., etc. That's kind of the math behind it. So if we can get to this point, we're in great shape. We can start graphing this stuff like that. Okay, well, that's what the streamline function is all about. Okay, basically, if you have a streamline function that looks, say, just making up an example like this, x squared minus y squared. You can think of this portion right over here as essentially a streamline expression. And once we know this, we can take this expression and set it to various values of c and start graphing. So in this case, like if you had a streamline function like this, you would know that the streamlines for this flow have the form x squared minus y squared is equal to c. If our goal then is to graph, we can start graphing that by doing various values of c. And of course, maybe we can start out with something real simple and get a few lines. All right, well, that leads us to our first example. If you need to do this example, if you need to refer back to the notes from last lecture or pull out chapter 6, that's just fine. Let me get this example up there, and we encourage you guys to write it down and get going. So this is example 2. Per usual, we've got 2D flow. We've got a stream function, which is x squared plus y squared. And the unit of the stream function is feet squared per second. Okay. Our goals in this case is we're going to try to graph 3 streamlines in the xy plane. Then we're going to try to get the dilation rate. And the dilation rate allows us to say, hey, what's going on? Is this fluid spreading out? Is this fluid compacting? Is the flow compressible or incompressible? Okay, then we're going to try to get the rotation rate. And a huge question in fluid modeling is whether the flow is irrotational. Okay, and then finally, the last thing that we're going to try to do is come up with an expression for the velocity vector and maybe add a couple of velocity vectors. So 4 parts to this problem. Again, I encourage you to stop the video and make as much progress as you can. I'm going to go through it step by step on the whiteboard. So hopefully you're drawing an XY plane and you're writing down something like x squared plus y squared equals some number. You've seen this one before, so I would encourage you to do something very, very simple and get a graph up there. So get going on that. Okay, so I know my streamlines have the form x squared plus y squared equals some number. And hopefully you remember that if there's a number over here, this equation indicates that we get a circle. So we have fluid flowing in a circle. Now let's just pick a really easy number. The number over here is the square of the radius. So I'm just going to do 1, x squared plus y squared equals 1. And now I can start graphing. And obviously, if you had time, you could use some sort of graphing program to make this look really neat. But for today, we're just going to try to get something up there. Okay, so bear with my circle. That's really, really poor. But if I make this constant over here equal to 1, I get a circle of radius 1. All right, well, then what we would probably, the next thing is, at least in my mind, the easiest thing to do is to do x squared plus y squared equals 4. That's a circle of radius 2. Okay, and then I'm just going to try to get something that looks something like a circle. Again, I wish my artistic skills were better, but we'll just do that. All right. All right, and when to go? Again, I could do any numbers I want, but I'll just do 9 because that's a circle of radius 3. So I got a value over there, value over there, value up here like this. Okay, and I may be a little bit boring for some of you guys. We've done this example many times. What's going on here? We've got a 2-dimensional fluid and it is swirling about. Maybe it's a vortex or something like that. All right. And so some questions we haven't answered that we would like to eventually be able to answer. Okay, first of all, in what direction is that swirl going? Is it going clockwise or is it going counterclockwise? We don't know. We know that we have elements going around in a circle. Okay, is there dilation? Is the fluid spreading out? Is it getting more compressed? Or is it an incompressible flow or flow without compression? Is there rotation? I believe the answer is going to be yes. Okay. Finally, where are those velocity potential lines? Where are those velocity potential lines? Or is that even possible to do? And we're going to come back to that later on. Okay, and we'll try to get a couple of velocity vectors in there. All right, so here we go. Let's go ahead and get going on the dilation rate. So dilation rate is a matter of doing du dx plus du dy. Okay, that's how we calculate the dilation rate for a velocity vector. But unfortunately, we don't have the velocity vector yet. So you have to go back and remind yourself how to get the velocity vector. So this is the stream function right here. X squared plus y squared. Okay, so to get u, we do the partial of the stream function with respect to y. And the partial of the stream function with respect to y is equal to 2y. All right, and we also need v. So v is the partial of the stream function with respect to x, but you throw a negative in front of that, so it's equal to negative 2x. All right, so we got there. So there are the components of our velocity vector. There are the components of the velocity vector. All right, now, by the way, we're going to give you, when it comes to these partials, we're going to give you a vector calculus way to think about it. But honestly, for these two here, I would just memorize those equations. And every time you do a homework problem, maybe have a summary sheet where you can refer to it, and eventually it'll become second nature. But right now, just accept it that I encourage you just to accept that that's the way it works. All right, so now what we're going to do actually is take a look at this question about the dilation rate. Now let's see if we can just do it in our heads really quickly. So the partial of u with respect to x is 0, and the partial of v with respect to y is 0. So these two things, adding these two things together, we get 0, and so we get no dilation. We got no dilation going around. And that should hopefully make some sense to you. If I got this fluid and it's just going around and around and around like this, and there's no movement in or there's no movement out, etc., it should make sense that if I took a look at any little fluid element, it is going to stay with the same size and shape as it goes around. So it's not going to be spreading out, it's not going to be compressing. All right, so that's part B. The dilation rate is 0. And this is an example of flow without compression. The way your textbook is going to describe it is this is an example of incompressible flow. Okay, how about rotation? So give me a second just to erase a little bit. Okay, we've got our U function and our V function. I'm going to write those up above just to keep up with our U. Okay, so our U function is 2y, and our v function is negative 2x. Okay, got those back up there. All right. And then how about rotation? How about rotation? So in that case, actually, we do cross, actually, when we do rotation. So we're going to do dv dy minus du dx. Okay, dv dy minus du dx. And that actually is going to end up giving us the rotation. All right, so part C then was to take a look and say, hey, for this flow, is there rotation? And obviously there's going to be, but we'd like to verify that and also come up with a number. So that is called figuring out the curl of the velocity vector. And here's your expression for 2 dimensions if you don't remember it. Okay, so in mathematical terms, it might be helpful to remember that we're doing cross derivatives. A lot of times we do the derivative of v with respect to y, but here we're doing the partial of v with respect to x, and then we're doing the partial of u with respect to y. So that's the curl of v. It's actually a vector, and it is a vector which is thought of being in the z direction. So if you wanted to use vector notation, you would put a k hat at the end of that. And let's get at it. Maybe we can work it out in our head. So dv dx, okay? I'm getting negative 2 for dv dx. And du dy, I'm getting 2. So I'm getting negative 2 minus 2, and I'm getting negative 4 k hat. Okay, negative 4 k hat. So what that does, first question that we want to answer a lot of times is, hey, is the flow rotational? Is the flow, or is it irrotational? And the answer is going to be no, there is rotation. And this is close to giving us the rotation rate. If you're going to get the rotation rate, it is actually 1/2 of this. So we would say the omega about the z-axis is negative 2. And that actually is going to be radians per second. And then the idea is that in that case, we would actually take our thumb and point it in the negative z direction, and the rotation of our fingers on using the right hand rule would indicate that we have rotation going like that. So we got rotation going like that. Okay. All right, last thing, maybe let's add a velocity vector to it and see whether that's right. So our velocity vector at any point u equals 2y and v equals negative 2x. And I think it's easiest maybe to go to point on there actually. So I'm going to put a point on there and get the velocity vector and verify that's true. So I got that point right there, which is supposed to be x equals 2, y equals 0. So if y equals 0, the u value is 0, and v equals negative 2 times x, so negative 4. So we got a velocity vector like that, which is perpendicular to flow. My drawing is not very good, so we've got rotation. Okay, so that is really a review of where we were at the end of last lecture, with the additional idea of trying to get clearer on what this stream function is. If you have a stream function, we can think about this stuff over here as a streamline expression. We set that equal to various constants, and then we can start drawing. Okay, so before we move on, a little bit more about this vector notation and vector calculus. So I've given you formulas that for things like the curl and also the spreading out or the dilation of fluid flow field. And many times it's expressed in terms of vector calculus, and that may be helpful in some cases to remember what's going on. So a reminder on vector differentiation. When you're doing regular differentiation, you do ddx or partial with respect to x. But in vectors, we end up applying this operator right here, which is sometimes called the del operator. So we're going to do the del operator to various functions in different ways. So a quick reminder on that, okay? The first one is, the first way of doing it is called the divergence function, and we've already done that really quickly. So that is sometimes, if we're doing the divergence of a velocity vector, we could say, hey, we're doing the divergence of v, okay? And that is a lot of times expressed as del with a dot times the velocity vector, okay? And that one's pretty easy to work with. That's going to take a vector like velocity and give us a scalar. So in our particular case, it's going to be du dx plus dv dy. Okay, du dx plus dv dy. And if you go on and do a little bit more with this stuff, there's going to be a dw dz. Okay, divergence. Well, you can think about that as telling us how much our flow field is spreading out. How much spread out do we have of velocity? If the velocity vectors are not spreading out that much, then we don't have dilation. Dilation. We're going to use this computation here to work that out. Okay, the second thing is the curl. Okay, the curl. And so we've already done that, but giving you some ideas on vector notation. If we want to figure out rotation for a vector, we're going to do the curl of v. Okay, in this case, we end up getting a scalar quantity. Okay, in this case, we're going to get a vector quantity. Right? How is it written in vector calculus? We're going to take that del operator and do the cross product of that del operator with the velocity function. Cross product with the velocity function. Of course, you can pull out your calculus book and review this in detail. I'm being a little bit imprecise, but want to remind you of that. Okay, in our case, it's simple because we only have, we're only doing functions of x and y. So in that case, when we do the curl of v, we're going to do dv dx minus du dy. Okay, and I won't write it up there, but that is in the k-hat direction, actually. That's in the k-hat direction. And of course, that's equal to 2 times the rotation rate about the z-axis. 2 times the rotation rate around the z-axis. Okay, one to go. Hopefully from your multivariate calculus, there was div, there was curl, and there was grad, the gradient. So what's actually going on with that? So the gradient is going to take a scalar to a vector. So here we've got vector to scalar. Here we've got vector to vector. And then that is the last one, the gradient is going to go scalar to the vector. Okay, so if we have the gradient of a function, we could say we can do the grad of a function phi. Okay, it could be written that way. Okay, and then in del notation, there's no dot, there's no x, there's just del. So del of phi. Okay, del of phi. And how do you actually go about doing that? That's going to give us that is actually going to give us a vector. So we're just going to go x, y, z, I, j, k. Okay, dphi, and I did not do the k part. So we're going to do some gradient of functions in this class. And what we're going to do is we're going to do that velocity potential function. We're going to do the gradient of the velocity potential function. Okay, so we've done lots of stuff with the curl, and we've done lots of stuff with the divergence, even though we haven't called the divergence the divergence. But what about with the gradient? So let's just do a quick example and see if we can almost work it out in our head. So, or can work it out in our head. So I've got a velocity potential function, 3xy minus 4y squared. And what is the gradient? What is the gradient of that function? And so again, this maybe has something to do with pressure and how is pressure changing. Very rough? More on that later. But we'll just follow the math for right now. So what we're supposed to do is we're supposed to do the partial of this with respect to x as our first step. So this is going to be 3y, and that's going to be 0. So I've got 3y in the I hat direction. And then we're going to do the partial of this phi with respect to y. And I've got 3x here, and I've got 8y there. So I would just, to be neat, include in parentheses 3x. Okay, and then minus 8y there. Okay, and that would be in the j hat direction. And it turns out that gradient is going to be very meaningful for fluids. So if we have this velocity potential, doing this gradient is really going to help us out as far as understanding what's going on with that fluid. Okay, so we'll get back to work on an example in just a minute, but maybe a thought on how to approach all this work. There's quite a bit that is unfamiliar, and I think having a summary sheet in front of you would be a really good idea. So you might want to take a break and make a summary sheet really quickly, but you're certainly welcome to use my cheat sheet or summary sheet right now, what we have so far. So today we have a little bit more on the stream function. Which stream function is going to be a function of x and y, and what that allows us to do is graph streamlines. And in addition, get some more work. So we want to be able to go from the streamline function to the velocity vector, and there's our guidelines for two-dimensional, okay? And you should have that down. Okay, what else do we want to be able to do? Well, a lot of times we have the velocity vector, we want to come up with the acceleration vector. That's back in chapter 4. That's stuff that you should be confident with. So go back and take a look at chapter 4 if you don't remember how to do that. New ideas, we want to figure out, is there any spreading out? Is there any dilation? And that's doing the divergence function. Okay, and so for our particular case, the divergence function simplifies to that expression on the right there. And it is a scalar. It's telling us how much it's spreading out. Okay, and we can even come up with the units for that. In addition, we want to figure out whether the flow is rotational, which is a really big idea, and that's doing the curl of the velocity vector. And for us, it simplifies to that form. Okay, and then, of course, the last thing we would like to be able to do is start taking a look at this velocity potential, that function there, another function, and we're going to get to that towards the end of the lecture. All right, but just to make sure we're on track, let's do one more example, and I would love it if I could give you an example like this where I said, look, imagine you're teaching someone else, explain everything important about that particular example. But let me guide you through it again. We'll do the same 4 things. There's a stream function. Let's get 2 or maybe 3 streamlines. Note that x is greater or equal to 0. Okay, let's figure out if there's dilation. Okay, is this a case where flow spreads out, gets more compact, or actually is there no compression going on? Is it incompressible? All right, let's figure out rotation. Is it irrotational, or is there some sort of rotation rate? Okay, and then finally, let's just go ahead and put a velocity vector or 2 on that to try to make sense of it. All right, so I'm going to go ahead and pause the video and get going and work my way through that. Okay, so here's our example. We got a stream function that's equal to 2xy, and we're going to show what we know about it. But before we get going, just something that I'd like to mention. What you eventually would like to be able to do if you get into this is to know maybe like 20 stream functions. And then when you're supposed to analyze some sort of fluid flow, say like fluid going through a fan or a pump or over a car, et cetera, be able to say, hey, which stream function would be best? Or ideally, what is really neat is actually combining a couple different stream functions. So for example, if you had some water swirling and going down, what stream functions would you use? And that's one's not hard to come up with. You would actually combine a circular stream function with a linear stream function. So this is a combination of curling motion, circular motion, plus linear motion going down. And if you knew the 2 stream functions for that, you could combine them and then come up with a really accurate analysis of what's going on. For now, though, what we're going to do is essentially either give you the stream function or something like that and see if you can go through the analysis. So here we go. The first thing we want to do is graph it. And so what we're going to do is take that 2xy and set it to various values. So you can choose whatever you want, but my first one I'm going to do is I'm going to do I'm going to pick 2. Why 2? Well, it works out nicely mathematically. So what if we said 2xy is equal to 2? And we need to graph that. You don't need to solve for y, but in this case, that works out pretty well. I get y is equal to 1 over x, okay? And then I can graph that. All right, so what turns out then, x is greater or equal to 0, so I could set up an xy plane over here like this, and I just need to do the positive values. Hopefully you're doing a neater job than me because you're just looking down at your paper. Okay, and no need to be super precise, but go ahead and graph that function, and we'll see if we get a feel for what might be going on with this flow. Okay, you hopefully did much better than that if you have graph paper, but I got that this streamline goes to the point 1, 1. So that's that point right there like that. And I drew a curve with several points to say if it was over at 4, it would be 1/4. If it was 1/4, it would be 4. So I got something going on like that. So what is physically going on in this situation? To me, at least, I don't have enough information there. So I'm going to do another streamline. So trying to come up with something that was easy. If I did 2xy equals 4, that might be an easy streamline to do. And that's going to give me y is equal to 2 over x. And that I can graph as well. So I'll do another streamline in there like that. Instead, this would be at 1, it would be at 2. And then if I went over to x equals 2, it would be at 1. And you're going to see that you're going to get that pattern there like that as well. Okay, mistake there. I put an arrow there. I don't know which way this flow is going yet. Okay, but physically what's going on, okay? Physically what's going on, it might be like the x-axis and the y-axis are some sort of barrier, and this fluid is actually moving this way, encountering that barrier and moving up, or it's coming this way and it's going there to the right. We don't know yet which direction it's going. All right, hey, let's just do one more really quickly. And I'd like you to stop and think about that for a second. What are those graphs going to look like? What is the graph of that equation going to look like? Well, thinking about it, I could divide both sides by 2x, and I'm going to get y equals 0. So that would be the y-axis, all right? And then if I divided both sides by 2y, we get x equals 0. Pardon me, this would be the x-axis, and this would be the y-axis. So in a sense, there's like a line right there like that. And that's something just for you to think about a little bit of what's going on. All right, there's a good start. Probably would do one more streamline in there to get a good picture of it. What else are we supposed to do? Well, we're supposed to decide whether that flow is spreading out or not. So that's the dilation, okay? And that is doing the divergence of our velocity vector. So I'm going to write down the velocity vector really quickly because we're going to be using that quite a bit, okay? So to get the velocity vector, hopefully either have it memorized or you can refer to your sheet, okay? You're going to actually take the derivative of the stream function with respect to y. So that is 2x. Okay, and then you're going to do the derivative of the stream function with respect to x and put a negative in front of it. So that's going to be negative 2y times I hat. Okay, so there's our velocity vector, okay, sort of a mechanical step. All right, next thing we want to do is figure out, is there any dilation? And for that, we're going to do the divergence of the velocity vector. Okay, and that's going to take the vector, the velocity vector, and make it into a scalar, give us a scalar result. Okay, and so basically what I'm going to do in that case is I am going to take du dx and add dv dy. So du dx is going to be 2. dv dy is going to be negative 2. And so that equals 0. Okay, so our dilation is 0. And this flow is consistent with incompressibility. So the book is going to say this is incompressible flow. All right, next thing is rotation. So rotation, we're going to do the curl of the velocity vector. Okay, and the curl of the velocity vector is going to give a vector. In our case, we're really simple. So we are going to just have one direction. So we're going to do the partial of v with respect to the x minus the partial of u with respect to y. Okay. Partial of v with respect to x, partial of u with respect to y. Okay, and taking a look at that, partial of v with respect to x is 0. Partial of u with respect to y is 0. And so that is 0. Okay, so what the book is going to say, or anyone analyzing fluid flow is going to say that we have irrotational flow. We have no rotation. Well, that looks a little bit strange to me. How could that be a lack of rotation at that point? And I'm going to work on with you guys on trying to explain that a little bit. But one idea of that, if I put a little fluid element in there, is that as this fluid element moves, it's not going to rotate. That's what this calculation is saying. So it's kind of hard to see it from this point. Sometimes when I've thought about this type of stuff, I've said, well, okay, there's no rotation because this fluid's not going to return to the same point. If you have rotation, we sort of return to the same point. That's pretty imprecise. You're welcome to think about it, but for right now, perhaps the main interpretation is this fluid element does not rotate as it moves along. Okay, so what else do we have left to do? We've graphed it. We've gotten we've taken a look at the divergence. We've taken a look at the curl. We would like to do the stream function. We would like to do the velocity potential function, but we're not going to do that yet. We wanted to do is get a velocity vector and to see what's going on at some point. So I'm just going to pick 1, 1. Take a look at that. So I'm going to do v at 1, 1. And see if that makes sense, see what's going on with that. So v at 1, 1, that is going to be 2 minus 2, so 2i hat minus 2j hat. So at this point, essentially, we're going over 2 and down 2, so we'd be going at a 45-degree angle like that. Okay, and we could do many other points, but basically what we have is we have flow going like this. Every single flow is going like that. And so this might be like half of our pump problem, that we have some flow entering through a pipe, and on this side it ends up going there like that. And this stream function might be a good step as far as modeling what's going on. All right, so the second new idea for today is about this velocity potential function, this velocity potential function phi. And the first idea was, what really is that stream function telling us? It's giving us an expression that we can use for streamlines, and then want to work on what this velocity potential function is telling us. First thing I want you to recognize that the velocity potential function takes an input x, y, z, or r theta, etc., and puts out a number. So it puts out a scalar. That's going to be the result. So we had this example earlier. If you went to any point in the xy plane and put in the corresponding x and y, so if I go to, say, like 2, 1, and I put that xy in there, I'm going to get a number. So it's going to put out a scalar. What does that scalar mean? And what I would like you to do is, to start with, is just think about it a little bit like as something like pressure. And that's very imprecise, but I think it's good enough for us to get it going today. And to give you a little bit of feel for what's going on about that, when we think about cause of flow, if you're supposed to tell someone, someone who doesn't know much about fluids, why is there flow? Well, we started in chapter 1 with the most theoretical idea, is that flow is going to be caused by shear, and that's really good. The second idea is probably more common out there in industry, is flow is caused by delta P. Okay, so flow is caused by change in pressure. So to take a couple examples, okay, if this direction is south, okay, and we have a north wind, a wind coming from the north here like this, okay, and this is somewhere up like in Chico or something like that, and this is Sacramento. If you read the pressure here versus the pressure there, the pressure is going to be high here and relatively low there. It's very small. This might be 14.72 psi, and this might be 14.66 psi, but that's going to be enough to cause flow. All right, second example really quickly. We're going to get into pipe flow as we go further on in this course, all right? And if we have flow going this way in a pipe, and we have a gauge that registers pressure at this point and pressure at this point, this pressure here is going to be lower than that pressure there, and we're going to say it's the delta P that's causing the flow. All right, so that's a background idea really quickly, that delta P causes flow. The second idea is that the bigger the delta P, the bigger the pressure difference from here to here, the greater the flow rate is going to be. And that's something that's been observed in nature again and again and again, and has been made mathematical so that we can do some good design work. All right, so that's the first idea. Okay, the second idea is this idea again that this velocity potential function is kind of like pressure. So try and putting those two things together. If the cause of flow is change in pressure, then we should be able to get the flow by doing the rate of change of this function, the rate of change of this function. And in fact, that is the idea that we're going to use. If we want to get the velocity vector, we're going to do the derivative of this function, okay? We're going to do this derivative of this function, and that is going to be given by one of the three delta functions. There's the divergence, how much it spreads out. Okay, there's the curl, there's the how much the rotation, and there is the gradient, which is kind of like rate of change. So we're going to do the gradient of the velocity vector. And so that's simple enough. Pardon me, goodness, please erase that. We're going to do the gradient of this pressure, essentially. And please don't use that word pressure. I'm just trying to give you guys an idea. That's the rate of change of the velocity potential. So basically what we're going to do is do d phi dx in the x direction plus d phi dy in the j hat direction. And then if we were doing three-dimensional, we would have one more term. So you might want to write that down, that one way we can figure out the velocity vector is to do the gradient of the velocity potential function. Gradient of the velocity potential function. All right. Okay, and then last idea that we want to have is when we get all done with our analysis, we would like to have lines of constant phi on our graph. So we would like to say, okay, there's a certain phi value here, and there's a certain phi value here, and this is the same, and a certain phi value here, and this is the same, and we would like to connect those. So a little bit maybe puzzling to think about, but I think the thing to do is get in an example. So I'm going to pause the video and get an example for you guys to work on. Okay, so let's take a look at an example where we can show what we know. I've given you a velocity potential function. It's two-dimensional, so it's going to be in the xy plane, but only for values that are x equals greater than equal to 0. And what are some things we'd like to do in order to actually show that our understanding or to visualize that flow field? So with giving you a picture that we had earlier, what we would like to be able to do basically is get something like this. And if you remember earlier, the green, those were the streamlines. So we had this flow that was going down and making a turn to the right, okay? And then the red lines were the velocity potential lines. And basically you can see that if we look down over here, these velocity potential lines are closely spaced, which might mean something like the pressure is changing quickly and therefore there's greater velocity. Here they're widely spaced and those velocity vectors are really, really small. And then as you go over to the right, they're more closely spaced and the velocity vectors are bigger. So that would give us a good feel of what's going on. We've got streamlines, we got the velocity potential lines and equipotential lines, and then finally we have some velocity vectors. So we're gonna go through and do that. All right, again, you can approach this however you want. I, over to my right, have a summary here, and that's just basically adding a little bit to what we had earlier. including we have this idea that we can get the velocity vector by doing the gradient of this velocity potential function. And that is a pretty good summary of what we have right there. So maybe I should be a little embarrassed to admit that you're going to see me glancing to the side to look at that. I don't do this much type of work all that much, although I'm kind of at the point in my career where I'd be interested in making some change, making a little bit of a change and doing something different. When I went to graduate school, I was really interested in sort of like a bifurcation of two different things. I was really interested in the theoretical math and modeling fluids and heat transfer. And then I was also interested in very simple systems, which are low energy use, but in my mind, make a lot of sense. And I've had a couple cases which have come together over the years of my career where I've done some mathematical modeling that led to a design of a simple system. And for me, that's been some of the most satisfying stuff. Anyway, so let's get at it. So I'll take you through it, some things we're going to do on this. The first thing we're going to do is just go ahead and try to evaluate phi at a couple different points. So let's just go ahead and try to get what phi is at 2, 2. So for what if I went to the point 2, 2, what is that value of phi? Well, you just put that in there, and I get 6 minus 2, and right there it's equal to 4. Okay? That's a scalar value. What does it represent? We're not going to stress about it too much, but if you're thinking about it something like pressure, that's not a bad start. Okay, what about phi at 4, 0? Okay, what's that going to be like? Okay, so we're going to over to 4, 0, and we're putting 4 in there. It doesn't go anywhere. Put 0 there. We've got a phi value of 6. What does that mean? Not worrying about it too much, just trying to get a value for what idea for what that velocity potential is. Okay, so I'm going to erase that for now. I'm not going to use that for the time being and get at it. Okay, so what we would like to do is we would like to get the streamlines up there. Okay, and the first thing to do, Ben, is basically to get the velocity vectors to go ahead and do that. So let's go ahead and get the velocity vector, and that's going to involve doing the gradient of this. So I'm going to do the gradient of phi. Okay, and you can be doing it yourself. You're welcome to pause the video, but or follow along. I'm going to do the partial of this with respect to x, and that's 0. Okay, and I'm going to do the partial of this with respect to y, and that's -1. And there is my velocity vector. Okay, and maybe it's worth noting that the u is equal to 0, and the v is equal to -1. All right, so that maybe is enough for us to just stop and say, hey, good enough, I understand what's going on with this flow. For every point over here, like that point right there, there's no motion horizontally, and the motion is -1 vertically. So we've got flow going in the negative direction, and that would be true at this point right over here. There's no flow horizontally, and there'd be flow in the negative x direction. Okay, so that's a pretty good start, all right? But in addition, what we would like to do, okay, we've got the velocity vector, and we actually have it written in another notation here, is we would like to take a look about, is this flow compressible or incompressible? What's going on in that case? Try to answer in your head. So I'm thinking, okay, this flow right here is like -1, this flow right here is -1. If I put a little fluid element right here like this, is that element going to be spreading out or contracting or basically staying the same size? And I get that it is doing neither. So I'm going to say it's incompressible. Let's make sure that the math actually confirms that. So we're going to do the divergence of the velocity vector. We're going to do the divergence of the velocity vector. That's going to give us a scalar. And so that is du dx plus dv dy. Okay. And I'm getting that is 0 and that is 0. So I'm getting no dilation. Okay, so we got that done. All right, another thing that is going to be really, really important as we go through it is there rotation, or is this flow irrotational? So that we're going to do the curl of the velocity vector. Okay. And the curl of the velocity vector is, again, we got those cross derivatives. So it's going to be dv dx minus du dy. And that's going to be around the z-axis. And once again, we're getting, well, let's check ourselves really quickly. What if I have fluid that's going down here like this? Is it curling? Is it rotating? And I'm saying no, and the math reflects that. So it's not curling. Okay, hey, anticipation. we can write the velocity potential function only in cases where the flow is irrotational. So that's something that we'll be checking out later on. All right, we got that. So now let's just go ahead and get the streamline function so we can verify what the graph actually ends up looking like. So how are we going to get the streamline function? So that is, I would really encourage you to pause the video and take a look at your cheat sheet and saying, okay, given the information that we have so far, how are we going to go ahead and get that stream function? Okay, well, there's one relationship that we have, that the partial of the stream function with respect to y is u. We know for this function that u is always equal to 0. Okay, so that is going to allow us to say something about the stream function. Okay, the stream function, what would the antiderivative of 0 be? Well, it would be a constant. Okay, or strictly speaking, it could be a function of x, because the derivative with respect to y of a function of x is going to be equal to 0. All right, good. What's the other thing that we have? We know that the partial of the stream function with respect to x is equal to the opposite of v. Okay, and in this case, the velocity vector is always equal to 1. Velocity vector is always equal to 1. So we can go backwards there and get what the stream function is for that, and that is going to be equal to x plus some function of y. All right, good. All right, so we want to try to put those two together and get a single function that actually makes sense. So our stream function, it's got to have an x in it. Okay, and then does it need some sort of function of y? So we should check ourselves really quickly. If we do the derivative of this with respect to x and put a negative in front of it, we're going to get -1. If we do the derivative of this with respect to y, we're going to get 0. So that is our stream function, but we could have a constant in there. So that is our stream function. Okay, so we could say that our stream function is x plus c, where c is arbitrary, and and that would be a correct answer. Okay. One possible value of c that works for this case is to say the stream function is equal to x. Okay, there we go. So we got the stream function is equal to x. All right, so what are we supposed to do now? We want to fill up this graph with a bunch of lines to represent what's going on with this flow. And we know basically the flow is going down. We know the flow is going down. So let's get some streamlines. So phi equals x, we start making different values for x. X is equal to 0, x is equal to 1, x is equal to 2. So let's do that really quickly up here. Okay, I'll just put 1 up there and then we'll talk our way through it. What would x equal 1 look like? Well, x is equal to 1 is a vertical line through 1. Okay. Hopefully your graph looks better than me. Let's do x equals 2. That would be a vertical line through 2. Etc. X equals 3, a vertical line through 3, and x equals 4, a vertical line through 4, etc. So those are the stream lines. By the way, what direction is the flow going? Well, we had this earlier. We had v equals -1, so we could actually put in lines like that. Okay, so if you recall earlier, the equipotential lines, the red in that drawing, those are perpendicular to the green. The flow is perpendicular to the pressure gradient. That is rough and something that I need to try to make more precise with you guys. But let's try to go ahead and get there. Let's go back to this velocity potential function, 6 minus y, and think, could we visualize some sort of set of values for which this thing is constant? It's constant. Okay, well, let's start with y is equal to 3. So y equals equal to 3. So there's y equals 3. Okay, if I put y equals 3 there, I get 6 minus 3 is 3. And that's not going to vary anywhere along this dashed line here like this. So that is an equipotential line with phi is equal to 3. Sorry about my writing. That's an equipotential line which phi equal to 3. Okay, then I'll have an equipotential line at phi equals 2. I'll have an equipotential line at phi equals 1. I'll have an equipotential line at phi equals -1, etc. So in this case, the equipotential lines are perpendicular to the velocity lines and they're equally spaced. And so we have a constant change in you can think about it as pressure, although I need to do a better job with that. What we have no speeding up or slowing down. You can verify that with the acceleration vector. Okay, really good. I mean, that's the basics, okay? It's basically we're going to work with a stream function, the velocity potential function, and try to visualize the flow. But there's one thing that's a little bit unrepresented about this example, and that is that we started with the velocity potential function. And in general, when you take a look at a flow, okay, so we got flow going over a car, or we have flow going over for a pump, or flow going for a fan, your bag of tricks is going to be to start with the stream function. You know that you have possible stream functions. So let's do one more example where we give you the stream function and you try to put it all together. All right, so last example, we gave you the velocity potential function. In this case, we're going to give you the stream function. And it's similar, it's the example we did earlier in class, but we're going to extend it to see if we can include velocity potential in our final picture. So some things that we're going to try to do, we're going to try to graph the streamlines. We're going to get the velocity vector. We're going to try to get the velocity potential function. And then we're going to try to put 3 equipotential lines in this graph. So if you feel like you got it, you can go ahead and stop the video and see if you can do that sequence of tasks on your own. But another alternative is to go step by step. Try it, check with me, keep going. Before we get going though, just a little bit about that whole velocity potential idea. So again, roughly, it's kind of like pressure. Next time I'll try to be a little more precise with that with you. But can we come up with a velocity potential function? This is a fact you should know, is that we can come up with the velocity potential function if the flow is irrotational. So that's what we want to check out. As a preliminary thing. And in this case, we are going to be able to do it. Just taking a look at an example where we got some flow modeling, you can see back here, we do have rotational flow for sure back here. And it's tough to come up with pressure or turbulent flow. And that has been something that has been a point of progress over the last 50 years or so, is trying to be coming up with a better idea about what pressure is like with turbulent flow. And that might be something interesting if any of you feel like, hey, I do want to go into graduate school. I want to go on and do stuff where I have to calculate more complicated stuff. But for today, we're going to stick with something simple, so let's get at it. So what if we were trying to go through this? So again, what we're going to try to do is graph some streamlines. We did that earlier. We ended up getting lines going like that. So the flow was going like that. All right, so we'll keep that in the back of our mind. Okay, what about the velocity vector? Well, I'll go through that work really quickly just to remind yourself what's going on. To get the velocity vector, to get the u value, okay, we're going to end up doing, pardon me, I got my cheat sheet in front of me. We're going to end up doing the partial of this with respect to y, so that's 2x. To get our vertical component of the velocity vector, we're going to do the opposite of the partial of this with respect to y, to x, which is -2x. So there's the information for our velocity vector right there. We got that. Pardon me for just a second. Okay, good. The next thing that we wanted to do on this example is see if we can come up with a stream function. So see if we can come up with a stream function. So taking a look at that and looking at your information, okay, the velocity vector, just a quick reminder, is the gradient of the velocity potential function. I'm sorry, I think I misspoke. I said we want to come up with the velocity potential function. So the gradient of the velocity potential function is equal to, pardon me, the d phi dx times I hat plus d phi dy times j hat. Okay, so hopefully you have that in your notes and you can see, okay, also the gradient of the velocity potential function is the velocity vector. So this is the velocity vector. So it's got to be the case that these two things are equal. d phi dx has to be equal to 2x. What are we after? We're trying to figure out phi, so we're going to do an antiderivative. So our velocity potential function phi has to be equal to x squared. And then it could have a plus 7, or it could have a plus 9, or it could have a plus y, or a plus sine y. So in general, it could have a function of y. So we write that down. By the way, if you guys want to take a look at this and just immediately go to what the velocity potential function is by thinking about it, that's just fine. I'm doing the more meticulous approach. All right. Then it also has to work for y. So goodness, I'm sorry, you guys, I have a mistake back here. The u is equal to 2x, and the v is negative 2y. I'm sorry about that. I hope some of you guys caught that in class. I'm sure there'll be a lot of hands raised. So there's been some really good participation in that regard. Okay, so d phi dy is equal to negative 2y. Okay, so according to that antiderivative process, we would have negative y squared. And then we could have a plus 4 or a plus a million, or we could have any sort of function of x. Okay, so what does our function have to have in it? It has to have an x squared and a y squared, and maybe it could have some other stuff. Let's just write what we have down and see how close that is to right. So phi is equal to x squared minus y squared, and maybe there could be some other stuff. So let's take a look at that and see if that works. If we do d phi dx, we get 2x, good. If we do d phi dy, we get negative 2y, but there could also be a constant, so I'm going to write that down there, plus c, where the constant's arbitrary. There doesn't need to be anything else. In fact, there cannot be anything else for this function to work. So there's our answer. There is our velocity potential function. All right, we want to graph that velocity potential function up there, but strictly speaking, that's ambiguous. That's not a clear instruction. We want to graph lines where this function is constant. So x squared minus y squared plus c is equal to some other constant. And that constant is arbitrary. We want to pick constants that are convenient. So basically what I encourage you to do is, if there's some sort of constant here, just focus on this stuff right here. Because you'd have x squared minus y squared plus a constant equals another constant. It's all x squared minus y squared equals a constant. So let's see if we can do some easy ones really quickly. So what's the easiest value of c you can come up with? We want to graph it. We want to make life as simple as possible as we can for us. What's the simplest value? Well, that's going to be 0. So can you graph the equation that says x squared minus y squared equals 0? Well, doing some solving might be one way to approach it. So I'm going to actually say, look, that's equivalent to y squared is equal to x squared. Right? Could I graph that? Well, we can do the square root of both sides. That's legal. So I would get y is equal to plus or minus x when I do the square root. And so hopefully you can take a second and visualize, hey, what's that going to look like on this graph? What's that going to look like on this graph? And y equals x is just a diagonal line, right? A 45-degree line. And y equals negative x is the opposite. So I'm going to have a line that goes at 45 degrees across like there. And that's one equipotential line right there like that. It would extend over here like this, but we just need to do x is greater or equal to 0. Okay, there would also be another line there going like that. But if you remember earlier, our streamlines were lines going like this that were just above the x-axis. So all we need to do is that. Okay, I was saying that we were trying to get 3 equipotential lines. So we've got one that's relevant to our flow. Let's just take a look at x squared minus y squared and see if we can think about another easy number to work with. Okay. So, by the way, you might be feeling a little intimidated by this. We're going to keep these values really easy for now. And anything you'll be asked to do on a quiz or test is going to be pretty straightforward. And we'll give you some practice on it. But practice is key. You know, if you take a look at the scores for chapter 6, test 1, the chapter 4 problem, we had a huge range with some people getting more than a perfect score and some people really, really struggling. And you know, again, that was a homework problem with a negative change to a positive. So basically, it was identical to a homework problem. The homework problems should help. So anytime you can spend on homework is going to be helpful. Okay, well, it turns out that if we could make this number over here a perfect square, then it's going to be a little bit easier to work with. So I encourage you, let's just try it for 9. You could try anything, but 9 turns out it works out great. All right, so we're going to try to see if we can solve that equation and graph it. So many of you guys know what that equation is. That's the equation of a hyperbola. But let's just say we didn't remember that and tried to come up with it. So what if you solve that equation for y? So basically what we would do is we would take the y and move it over here, and take the 9 and move it over there. So I would have y squared is equal to x squared minus 9, and y would be x squared minus 9, the square root of that, plus or minus. Okay, so let's go ahead and start graphing that. We can start putting x values in there and see what it looks like. I'm going to change colors pins because I'm going to go up to the graph. All right, and y equals x squared minus 9. I put 0 in there, and I get 0 minus 9 is a negative number, so I can't do that. What's the smallest x value we can put in there? Hopefully you can see it's 3. So if we put in 3, we get a value of 0, and that works out pretty well. So then we can keep graphing. We could put in 4, we could put in 5, we could put 6, etc. Okay. If you put in 5, that's a really convenient one to do. So I'm going to put in 5 in there. And so I get what? 25 minus 9 is 16. So at 5, I'm going to get y is equal to 4. So I'm going to go over to 5, and I get a value as 4, which is a little bit below that line. And if you took your time and graph, you would end up getting this part of a hyperbola. Oops, I'm sorry, I was going to do dashed lines for my equipotential lines. I get a hyperbola like that, which is getting closer and closer and closer to that diagonal line. Okay, hey, so now I have 2 equipotential lines, and I would like to get one more. The third one can come from taking this equation right here and solving it for x. So I encourage you to try that on your own. See if you can solve that equation for x and think about what the line's going to look like. Okay, so we want to get one more line here, and it turns out that what we can do is we can solve this equation for x, but to make it work, actually, we need to change that 9 to a negative 9. So why don't you give it a try? Try to solve that equation for x and see how it works out. Okay, so there's my math. I got x squared minus y squared equals negative 9. Okay, and so then I can move the y squared to the other side, and I get x squared equals y squared minus 9. So x would be plus or minus the square root of y squared minus 9, and we're just going to do the positive one and start graphing. So again, we can put in various values of y and see how x turns out, and hopefully again you see that the smallest value you could put in there is 3, and so when y is equal to 3, x would be equal to 0. So that's going to be a point, a corresponding point up here like this. Okay, and hopefully you can, if you think about it some, what you can see is that we're going to get that other side of the hyperbola here that's going here like this, and it's getting closer there like that. Not a great drawing, and I don't need an arrow on it. So this is an equipotential line, this is an equipotential line, this is an equipotential line, and if you look back to our graph, we actually got streamlines that were going like this. Okay, and so we would have a complete picture here where we have flow going like this, and we have something due to like pressure going like that, where every one of these dashed lines is perpendicular, and that gives us a good feel for what's going on. Okay, I grant you that this is a little bit abstract, but next lecture, I'm hoping that we can make it a little bit practical, but regardless, try to get that idea. Look, you are going to eventually know a bunch of different stream functions, or a bunch of different velocity potential functions. And if you look at a physical situation like some flow, actually approaching node obstruction. That flow has to go up and over that obstruction. And how are the velocities going to work out? How are the potentials going to work out? Are we going to get rotation, et cetera? You can go to your bag of tricks and say, okay, I can use this particular function or combine those functions. For starters, though, I think make sure you've gone through this lecture and feel pretty confident about it. And then homework number 7 should be posted soon. And with some good practice on it, I think you'll be ready to do a little bit more realistic stuff with this material.